Hello everyone, my name is Ichi, and today I'll be presenting our work, titled Balanced Rate Distortion Optimization in Learned Image Compression. Before diving into the details, here is the outline for the presentation. First, I'll start with some preliminaries, as well as the challenges associated with current rate distortion optimization. Next, I'll move on to our method. Then, I'll discuss the experimental setting and experimental results. Finally, I'll wrap up with our conclusion and future work. Here is a simplified illustration of the standard practice of learned image compression. To optimize the LIC process, this is typically formulated as a rate distortion loss function. During training, the model parameters are updated using gradient descent. The update at each step combines the gradients of the rate and distortion terms. The standard method sums the gradients of the objectives. However, this can lead to an imbalance where the gradient from one objective dominates the update direction. To illustrate this issue, I'm showing two comparisons. In plot A on the left, we see the testing loss trends for both the standard RD optimization, dashed lines, and our proposed balanced RD optimization, solid lines. The balanced method achieves smoother and more stable improvements in both distortion and BPP. In plot B on the right, we compare the loss improvement speeds. The balanced optimization leads to a more consistent and less volatile improvement speed across epochs, while the standard approach shows much larger fluctuations and instability. To address the imbalance, we propose a balanced rate distortion optimization framework. Instead of simply summing the gradients, we reformulate the rate distortion optimization as a multi-objective optimization problem. We define the loss improvement speed at step T, where alpha is the step size and dt is the update direction. We want to seek an update direction dt that maximizes the minimum improvement speed between rate and distortion. This leads to the following saddle point formulation. We can solve the problem by applying the Lagrangian duality theorem and get the optimal update direction. By substituting the update back, finally, our task reduces to finding the best weights WT at each step. We proposed two solutions for solving the problem. For our solution 1, we use a course-defined gradient descent approach. We update the gradient weights, WT, iteratively, using the following update rule. WT plus 1 is WT minus alpha W tilde, where tilde delta is the gradient of our objective with respect to the weights. Using a Taylor expansion, we can relate the change in our loss values over each update step. And our solution 2 recognizes it as a constrained quadratic programming problem and applies the KKT optimality conditions. After computing WT, we update the model with the weighted sum of the log gradients. Overall, our approach allows us to efficiently decrease the rate and distortion objectives more equitably. For the experiment, we use COCO train set. We random crop 256 by 256 patches during training. Test set is Kodak, Click, and Technic. The anchor is VTM18. We use BD rate to access the performance. This shows the RD curve of these methods. As can be seen, our method consistently outperforms standard RD optimization at all RD points. Here are the BD rate results of the proposed method. Solution 1 is the course-define approach, and Solution 2 is the QP approach. Both solutions achieve an improvement over the standard approach, around 2.5% BD rate improvement for Solution 1 and around 2% BD rate for Solution 2. To summarize, we addressed the imbalance issue in RD optimization for LIC by reframing the problem as a multi-objective optimization problem. We proposed two practical solutions to tackle this challenge. First, a course-defined approach that follows the standard rate distortion optimization trajectory. Second, we presented an analytical quadratic programming method that solves for the weights using the KKT conditions. For future work, one is to explore the efficient Tigepath scalarization approach to reduce the computational complexity. Another is to investigate projection-based methods for constraining the weights within the probability simplex. Thanks for the attention.